In this video, we will be looking at the 12 base functions. And once you become efficient at graphing each base function, then we will move on to transformations like shifting the base functions or stretching, compressing, and reflecting. So the first function we're going to look at is the grade 9 linear function, which is just y equals x, or in function notation, f at x equals x. So if you look at the table of values, I've picked x values from -2 to 2, which is pretty standard. And when in doubt, use these values so that way you get a nice range of negative and positive values. And because our function just tells us that whatever x is, that is what y will be. When x equals -2, y equals -2. When x equals 1, y equals 1. So when we end up plotting these points, we get this nice diagonal line. And a nice connection of a linear function is the connection to inverse relations. When you have a function and you reflect it over the line y equals x, you end up with the inverse. So a nice little flashback to that. Now for a line, our domain and range is infinite, so x is an element of all real numbers and y is an element of all real numbers. And for the key points, I just put those 5 points that we had in our table of values, but you could have also just used the middle 3 points from -1 to 1. Now for the properties, you might see more things that are interesting. These are the two main things that I wrote, which are that y matches whatever x is. So if x was 100, the y coordinate's 100, and that it's a line. And that's it for a line. Now we go to grade 10 and we look at the quadratic, which has the equation f at x equals x squared. So I took a few more x coordinates. I included the -3 and 3 as well. And all I'm going to do with my x values is square them. And a thing to remember is that even if you take a negative number and you square it, it becomes positive. So we end up with this parabolic shape that is all above the x-axis. And if you remember from grade 10 that your parent parabola has a original step pattern. So from the vertex, if you go to the right, you go up 1. Then to the right one, up 3. To the right one, up 5. If I went to the right one again, I'd go up 7. So that original step pattern was 1, 3, 5, 7, 9, all the odd numbers. And that was a shortcut that we used to graph our parabolas. Now the domain and range, the domain is still x is an element of all real numbers, but because we have that vertex, there's a minimum value now, so our range says that y has to be greater than or equal to 0. And for the key points, I put the central 5 points. Really, when you're graphing this, you can square any number in your head if you scale it larger or smaller, if you have to expand or make your parabola smaller. So for the key properties, I wrote that it's a parabola. The vertex is at 0, 0. It opens up, so there's a minimum of 0. That's your optimal value. And the axis of symmetry, that's that vertical line that cuts the parabola in half, has the equation x equals 0. Now, let's look at some new functions. And one that naturally goes next is the cubic function. So instead of x squared, we now have x cubed. And we know if we take a negative number and we raise it to the power of an odd number, it will stay negative. So if we look at our values, we have some negative values and some positive values. And I've just taken these x coordinates and cubed them. So now we have this type of shape. So it's not all in the positive region. And because we have it extending to the positives and the negatives, our domain and our range are both an element of all real numbers. So x is an element of all real numbers, y is an element of all real numbers. No restrictions at all. And then for the key points, I just chose the values from -2 to 2. And when you're graphing this to become more efficient with it, you don't have to create the table of values on the side. In your head, you can just do, okay, -2 cubed, that's -8, plot the point. 3 cubed is 27, plot the point. You don't have to create the table of values. You can pretty much do the table of values in your head. Now, some properties. It's just that it's cubic. Maybe you see more that is interesting about it, and you're more than welcome to jot that down. Next, we will look at the square root function. So the square root function, we have some things that we have to remember when we create our table of values, because notice I didn't pick any negative values. I didn't use that typical -2 to 2. Instead, I chose numbers that would be easy for me. Because I know that my function tells me whatever x I plug in, I have to square root it. That tells me right away I cannot put any negative values in my table of values because I can't take the square root of a negative number. And it also tells me that I don't want to pick some numbers because off the top of my head, I don't know what the square root of 5 is. I don't know what the square root of 3 is. So for my x values, you might notice I only chose perfect squares. That way, when I square root them, I get a nice integer value. The square root of 9 is 3, the square root of 16 is 4. I didn't pick any of the in-betweens, and that's okay. I don't need every x value to get the shape. So what it ends up looking like is something like this. And my key points are at 0, 1, 4, and 9. Those are usually the ones that will fit on our scale. And you can just square root those numbers in your head, and there you go. Now it might look like half a parabola to you that has been reflected. And if we remember our inverse connection, we knew that the inverse of a quadratic was a square root and vice versa. Now for our domain, we notice that there isn't an arrow on this end of our square root, which means we have to place a restriction. Nothing is going on in the negative side for x, and nothing is going on in the negative side for y. So for our domain, x is an element of all real numbers, but x is greater than or equal to 0. And same thing for our range. Y has to be greater than or equal to 0. My key points, I just put 0, 1, 4, and 9 because I can square root those easily. And that's another reason I don't pick those in-between values, because if I want to graph it efficiently and really quickly, if I don't know the square root of 3 or 2 off the top of my head, I'm just wasting time. Now for my properties, I just made some notes that you can't square root a negative. It's the inverse of half a parabola. And something that's important, only one side continues with the arrow, and 0, 0 is an endpoint. So just going back to our graph here, this will continue forever, but right here, it stops. It was not going to extend downwards at all. So that's something important to note. And again, that's because you can't square root a negative number. All right, let's move on to our cube root function. Now, with the square root function, we cannot square root a negative number, so I have that restriction. But I can cube root a negative number because odd index values are okay. So I again try to think of numbers that I can cube root easily in my head without going to the calculator. So if I take the cube root of -27, that's -3, because -3 cubed is -27. And honestly, if you can't think of the cube roots off the top of your head, just go backwards. Put the y coordinate first. So if I take -2 and I cube it, I get -8. So naturally, the cube root of -8 is -2. Or I can take 1. 1 cubed is 1, so the cube root of 1 is 1. So that's how I built this table of values. And these extreme values here with the 27s, those aren't going to fit on my grid. So really, it's these central 5 points that I will need. And if you look at this function when you graph it, it looks like the cubic function, but it's kind of the inverse of it because it's on its side. So our domain and range is still infinite. So x is an element of all real numbers, y is an element of all real numbers. There are the key points, like I said. And for the properties, I mentioned you can cube root a negative, so that's why we have that infinite domain. And like I said before, that the cube root function is the inverse of the cubic function. Okay, let's go to the absolute function. So these symbols here that look like little vertical sticks, those are your absolute signs, and anything that is within those absolute signs will turn positive. So I picked my typical x coordinates, -2 to 2, because there's nothing really special that or anything that restricts my x values here. So the absolute value of -2 is +2. The absolute value of -1 is +1. If I had -10 in there, the absolute value of -10 is +10. So you will notice here's a regular line, just like our base linear function y equals x, But here, instead of continuing down on the diagonal, this side here kind of goes up because the y coordinates must be positive. So it ends up looking like this little V with two linear components. Now the domain is still x is an element of all real numbers, but unlike our linear function that had an infinite range, because of that V shape, everything has to be above 0. So y is greater than or equal to 0. Then I put my 5 key points that were in the table of values, and then I just made a note about the shape, which is that it looks like two linear equations that are connected, so it has that V shape, and it's always positive. For the base function, now the minute you start shifting things around, it can go in the negatives, that's totally fine, but the base function is always positive. Now, let's go to a rational function, and that is when we have a fraction and we have a variable in the denominator. So our rational base function is 1 over x. Now you will see the typical x values that I've regularly placed, but I also put -1/2 and +1/2 to get a little bit more detail. So when I put -2 in, that would become 1 over -2. When I put -1, 1 over -1, which is -1. And if I just used those values, I would only have these 2 points, which don't guide me enough. So I also wanted to see what's going on between 0 and 1 so I know what path to follow. So if I put -1/2 in, I'd be doing 1 over -1/2, which simplifies to -2. And if I put an even smaller fraction, maybe a quarter, then I would have 4. And I'm just going to keep getting higher and higher. And then when I try to plug in 0, I know I can't do 1 divided by 0. So I end up with this asymptote on the y-axis. So my function will get really, really close to the y-axis, but it won't hit it or touch it. And same thing here, if I continue and I do 1 over 4, 0.25, 1 over 5, 0.2, and I can keep going, and anything, 1 divided by anything, it can get really, really tiny, but I'm never going to hit 0. So we end up kind of creating this curve between the x and y axis. And then same thing on the other side. There it is. So we do have some restrictions because of these asymptotes that are created on the x and the y axis. So for the domain, x is an element of all real numbers, but x cannot equal 0. And for the range, y is an element of all real numbers, but y cannot equal 0. And for the key points, I placed everything that was in my table of values. So I have a few more points here. When I graph it, I like to include when x is 4 and -4 as well, and also a quarter, just to get a few more points to make it a little bit more accurate. But as long as you have 3 on each side here and you get that nice curve and you follow the asymptotes, you're okay. Now for the key properties, I mentioned what an asymptote is, which is a line that a relation approaches but never touches, just for a reminder. Your vertical asymptote, so this line here, is x equals 0, and the horizontal is y equals 0. And those fit perfectly with our restrictions. Now let's go to the exponential. Now for the exponential base function, I have 2 to the power of x. But that base can be anything. You can have 3 to the power of x, 5 to the power of x. And in that scenario, you'd kind of have to create a table of values in your head to get the base function going. But we will do the base function for 2 to the x. And I just picked the values from -2 to 2. That's usually enough. I put 3 in here as well, but -2 to 2 is plenty. So when I do 2 to the power of -2, if we remember what negative exponents do, I'm just going to make a little side note here. When you have a negative exponent, you bring it down into the denominator to make it positive. So I really have 1 over 2 squared, and that's why we have a quarter. Then 2 to the -1 becomes a half. Anything to the power of 0 is 1, so this point here is going to be constant for any base. And then 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and you can do this with any base, just in your head, and plot the points as you go. But you end up with this kind of shape. For some bases, it will be steeper. For some, maybe a little more shallow, but here it is. And what you will notice is that one side will extend forever. But this right here, if I go to any negative number, 2 to the negative 10, 2 to the negative 20, I will get a really, really tiny number, but I will never ever hit that x-axis. And you can try it in your calculator or use your knowledge of negative exponents. If I had 2 to the negative, let's say 2 to the negative 20, all that would do is make me take a reciprocal, and 2 to the 20 will be a large number, and 1 divided by a large number is 0 point something. I'm never gonna get into the negatives. So we actually have another asymptote, but just one this time. And in our function, on the right side, it will continue forever, but on the left side, it will approach that asymptote. So for my domain, x is an element of all real numbers because we can see it extends forever to the right and left. But for our range, and something that's important to note here, it is just y is greater than 0, not equal to 0, because there's no way, no number you can plug into your function to make it equal 0. Then I put my nice key points from -2 to 2. And for my properties, I made a note that anything to the power of 0 equals 1, so that's just good for any base function, any base you put into your exponential. And that just means you're always going to have a y-intercept of 0, 1. I made a note that the horizontal asymptote is at y equals 0, and that there is an asymptote because there is no exponent that will give you a negative number, or 0 for the y value. All right, here's a function that we've never seen before. It doesn't look familiar, and that is your floor function. The floor function is quite interesting in that if you put any number into the function here, it's going to lower the number to the closest integer. So if I put 2 in, it's just going to become 2 because it's already an integer. But if I put 2.2, it's going to drop down to 2. If I put 2.5, it still drops down to 2. If I put 2.75, which we would normally round up to 3, the floor function drops it down to 2. If I put 2.9999999, it becomes 2. And we have to be careful with negative values. If I put -2.4, if I go to -2, I'm actually going higher. So -2.4 will become -3. So if we look at the table of values, to be honest, it's not the most helpful in drawing our graph, but I just put these values in so that you see that the values are dropped down. So -1.5 drops to -2. -0.5 drops down to -1. And then the positive values are a little more self-explanatory. What I really want to look at is our actual graph here. If I look here, any value between 0 and almost 1 will get dropped down to 0. So 0.5 will get dropped down to 0. 0.9 gets dropped down to 0. The minute I hit 1, though, my y-coordinate would be 1. So notice there is a hole here, which shows that there actually isn't a value when x equals 1 on this line. It jumps up over here. And then if I put 1.5 in, it drops down to 1. 1.9, it drops down to 1. And then again, when I hit 2, I have a hole on this line, and it jumps up over here. And now all of these values from 2 to 3 will be 2. But there's a hole at 3, and we jump up. So we end up with this nice little staircase where the ends are all holes, because on a specific integer, like at 7, there is no value at 6. It jumps up to 7. So there's a hole at the ends, but closed on the left side. And if we look at the negatives here, we can just continue the pattern, or we can think about anything between 0 and -1 will drop down to -1. Anything from -1 to -2 will drop down to -2. So like -1.5 will drop down to -2. And then you can continue that pattern to create this staircase. And really, to become efficient at graphing it, you just have to remember your first step. And your first step from 0 to 1, it drops down to 0. So there's the step. And then after that, you just follow the staircase, and remember that there's a hole on the right and it's closed on the left. Now, our domain and range, it's a little more interesting. The domain, we can see it goes on forever, And this is a function because if you do the vertical line test, let's say right here, there's only one value when x equals 2 because this is a hole and that's closed. So x can be anything, but for our range, our y values, they can only be integers, so y is an element of integers. For the key points, I just wrote start at 0, 0, and draw steps, 1 unit in length and 1 unit apart, just to remember how to graph it. The properties, it looks like a staircase. I mentioned that the left side is closed, so it includes that value, but the right side is open, so it doesn't include that value. And that's it for the staircase or the floor function. Next, we have a semicircle. And here we have the square root of 25 minus x squared. And if you look at the graph, you can see that the radius is 5. Now, it can be anything. It doesn't have to be 5. It really depends on this value here. Now, I just want to make a little note and a little reminder about the equation of a full circle. And if we remember from grade 10, a full circle had the equation x squared plus y squared equals r squared. And this base function for the semicircle, it looks like the x has been brought over to the other side. So r squared minus x squared, and then the square root of each side has been taken. Now the only difference is usually when we square root both sides, we get plus or minus. And if I had plus or minus, then I'd get a full circle. And then it wouldn't be a function anymore. So this is a semicircle because you don't have the plus minus, but something nice to know is that this value represents the radius squared. So looking at it right away, you know what the outside boundaries will be. So in my table of values, I just put -5 and 5 because those will be the extreme values here. And when I plug them into my function and I do 25 minus -5 squared, that would be 25 minus 25, which is 0. And that's why those points are on the x-axis. And if I put 0 in, I'm just taking the square root of 25 to get 5. So those are my outer boundaries. And I really don't care about what values are in this area. Now, like I said before, the radius of the circle doesn't have to be 5. If I had, for example, the square root of 36 minus x squared, I'm asking myself, what number squared is 36? That's 6. So my radius would be 6. Or if it had been 81 minus x squared, I know my radius would be 9. So for the base function, it doesn't just have to be a radius of 5. So keep that in mind. All right, so in this scenario, my domain is going to be from -5 to 5 for my x values, and my range will be from 0 to 5 because it is just the semicircle. I wrote down the points for my table of values for the key points, and for the properties I mentioned, it is a semicircle. It comes from the equation x squared plus y squared equals r squared, but the y is isolated for, and I mentioned it's only half a circle because the square root is not plus minus, which I showed you above. Now the last two functions are our trig functions, so sine and cos. The key points for the sine functions are every 90 degrees, and for this we're just thinking of our Cartesian grid, and we know the key points on your circle are the outer boundaries, so that's at 0, 90, 180, 270, and a full rotation is 360. That's why the key points for my x values are every 90 degrees. And if you plug those values in for x, you'll get the following y coordinates. And I don't want you to memorize this table of values. What I want you to remember is that sine begins at 0, so at the midline, and it goes up and then follows that wave function. So it starts at the midline, goes to the maximum, midline, minimum, midline. Now, this does continue forever, which makes our domain x is an element of all real numbers, but for our range, we're always going to have restrictions based on the max and mins, so from -1 to 1. I put my key points and some properties. We're going to use that trig terminology. So it is periodic, the period is a full rotation, which is 360, the amplitude is 1, and the midline, or your central axis, is at y equals 0. And again, just to show you how quick it is to graph, you start at the midline, follow the wave, and your key points here will be every 90 degrees, And as long as you remember your max and mins are 1 and -1, super quick to graph. Now let's move on to cosine, which is almost identical. Again, same key points for the x values. The only difference, when you plug them in, you start off at your maximum and then do the wave going downward. So max, midline, min, midline, max. And then your properties will be the exact same. Same domain and range, same key points for your graph in terms of the x values. The y's will be different because of the different starting point. And then the period, amplitude, midline, all the same. And again, to show how quick it is to graph, you start at your maximum, which is 1, and then make your way down. And these key points will be every 90 degrees. And that's it. Those are your 12 base functions. You're going to practice them so that you become really efficient at graphing them, so that we can then start transforming these functions.